Hello, everyone. Thank you for attending this webinar today. We appreciate your time. We're going to discuss using 3D scan data to recreate a propeller. We're going to do this using the scan converter utility in PropCad Premium. My name is Adam. I'm the lead engineer for PropCad. I've spoken with many of you. Some of you I haven't spoken with, but of course, as usual, if you have any questions, we can address them at the end of the webinar. And we can always address questions privately by email afterwards. In this presentation, we're going to discuss the new edition of PropCad, the PropCad Premium Edition, and we're going to discuss what's in the Premium Edition. Specifically, we're going to discuss the scan converter utility, which is one of the major features of the PropCad Premium Edition. We're going to discuss where scan data comes from, what the sources might be for the different scanning devices, and how that we take 3D XYZ data and convert it to 2D distributions and sections. We'll then do a demonstration of scan converter, and we'll discuss afterwards the best practices for using scan converter. We'll summarize what we've gone through today with some conclusions, and then we'll finish up the webinar with questions and the schedule and any other notices that we need to review. HydroComp PropCad 2016 has been broken into two different editions. There's the standard edition of PropCad and there's the premium edition. The principal features of both software editions is to do 2D drawings, 3D views, construction data, and export to CAD and CAM programs. It provides an automatic preparation of these documents, which are useful for propeller designers and builders and manufacturers. The premium version aims to support additional manufacturing and inspection operations within PropCad. We currently support over 150 users in 40 countries, and HydroComp is celebrating its 30th anniversary, or has celebrated its 30th anniversary. So we have quite a legacy of users in history. This is the interface of PropCad. Many of you have used PropCad before, so I won't spend too much time on it, but we'll just say that the principal parameters are entered for the propeller on the left-hand table. The major characteristics are summarized in the middle table. Data is viewed on the rightmost table, and the distributions, the blade distributions are shown in the sections table at the bottom. The scan converter utility is another utility that pops up on top of this window, and we'll discuss that a little bit later in this presentation. The major additional features that are included in the PropCad Premium Edition, the first thing is a floating network license, which allows you to work remotely. So you can have the license key installed on another computer and you can run PropCad on a different computer. The pattern corrections was the subject of our webinar last week, and you can watch that webinar from our website. Today we're going to review scan converter, and then there's a few more additional features that are included in the premium edition that we will go over in the future, in future webinars and things like that. The scan converter utility allows for the entry of scanned blade surface data in XYZ or polar format, and it converts it into a PropCad design file. The data typically comes from scanning or measurement devices, but it can also be obtained by interrogation of a 3D CAD file. What happens during this process is data is going to be sampled from the blade surfaces using either an inspection device, a drop probe, or actual from the orientation of the CAD file. We sweep a radial arc across the blade surface, and from there we extract XYZ points in 3D space. You can see that this cut in the propeller in the first image actually shows up as a 3D foil shape that's wrapped around a cylinder. PropCad will take this 3D shape, unwrap it, into a 2D section. And from there, it will derive chord, thickness, camber, pitch, cup drop, all the different parameters that we need to recreate this propeller inside of PropCad. The data for this comes from a variety of sources. Many of our customers are using PropScan and Hail MRI to do class-based propeller inspections. These systems can export the points that they're sampling, and these points can be used as input for Scan Converter. The next very common source of data is actually a table of 3D offsets, a printed report from a manufacturer or maybe from a publication that gives the offsets in 3D space. The last source of data, which here at HydroComp is probably the most common one that we come across, will be a fully digitized CAD model, typically an STL file or a STEP or an IGES file. These are generally created from high resolution laser scans or some sort of CMM based machine where they measure these points. They recreate the geometry in 3D space, and then we can interrogate that model to mimic the data that comes out of a Hail MRI or a PropScan. We'll show this process in a minute here. Scan Converter can take data in 3 different forms. The first form is a face thickness. We call it Scan Converter face thickness mode. What happens is we'll measure an ordinate on the face of the propeller, and then we'll get the corresponding thickness to the back surface. And this way we only really have to measure one side of the propeller and then take some thickness measurements. That works very well with the PropScan or the MRI because you don't have to necessarily flip the propeller over and measure the other side. You can just go through your inspection process and take a few thickness points in order to get all the data you need. If you are able to sample the back surface of the blade, we recommend using Scan Converter in face back mode. This allows you to enter separate ordinates for the face and the back. That way you don't have to measure thickness. You can do a scan of the face, flip the propeller over, do a scan of the back, and you can get all the data you need. This is often used with coordinate measuring machines, laser scans, etc. Ferro arms and different things like that we've seen used very successfully with the face back mode. The last mode for Scan Converter we refer to as blade mesh points. This actually takes a point cloud for the face and a point cloud for the back. It will sort the point cloud and automatically assemble sections out of the points. We use this. It's a faster method for pulling data from a CAD file, and we'll demonstrate this a little bit later today. So now I want to talk about a demonstration. In particular, this is a propeller that we have in our office here. It's been here for as long as I've been working here, and you can see we've doodled on it and used it for a lot of demonstrations. We had this propeller digitized, and we have a 3D model of it, which we're going to use to pull these points off the surfaces and input these points into Scan Converter. And lastly, we'll build the propeller model back up inside of PropCad. So without further ado, let's pull up Scan Converter. Well, let's actually start with our 3D model and discuss this whole process from start to finish. The first thing I'm going to do here is I'm going to pull up Rhinoceros, which is a CAD program that we use here in the office extensively for our work. And I'm going to open up the existing 3D geometry here. This is our data source. We're going to treat this as if it was a real propeller, and we're going to basically pull points off the surface and enter into Scan Converter. The first thing we need to do is pull some points off the surface. In order to do that, we need to choose an R over R position, intersect it with the surface, extract the curve, and pull some points specifically from that curve. To show you what I'm referring to, I'm going to turn on a few layers that I've prepared in advance. These cylinders are equivalent to R over R positions. And what we do is we punch these cylinders through the surfaces and create intersections at the boundaries between the cylinder and the blade surface. What that does is it will give us a curve. So I'm going to turn these curves on. I'm going to turn off the cylinder so you can see these curves. This is the path that an inspection probe would move across as it sweeps from the leading edge to the trailing edge. So we're just mimicking those paths, and we're laying those out on our propeller blade. What we do with this curve is we can take it and prepare points on the curve, and then we can use these points as input into Scan Converter. So I'm going to divide this into 13 points in this case. I hit enter, and we can see my points are now displayed. Let me make these a different color so we can really see them here. So hopefully we can now see these points on the surface. These are the input points for Scan Converter. This is just for one surface here, the back surface of the propeller as it would be. We could repeat the process again for the face in order to etch this curve and then add these points. These points all together look like this. And it's a bit difficult to see the points with the resolution on the computer, but hopefully you guys can see that we've etched points along each radial position. We can take these points and we can just export them. Each point has an XY position, XYZ position in space. And just to show you kind of what this data looks like, I've prepared an Excel file here. So this is the 0.7 or 70% of the radius here. We can see the layout of the face of the blade and the back of the blade here. This is the X versus Y perspective, essentially looking down on top of the propeller, looking down towards the hub. This is what we would see looking axially down the shaft. This is kind of how the data is laid out in 3D space. But you can see there's nothing special about this. It's just XYZ triplets, 3D data. What we need to do is take this cylinder here and unwrap this into 2D, a 2D section or a 2D airfoil shape so that PropCad can use it properly. What I want to do now is just show Scan Converter. So I'm going to go into the utilities here, and I'm going to pull the face back mode because we have separate points for the face and the back. You can see there's a bunch of initial data to set up. So we're going to set this up as millimeters, right-handed. It's a 3-blade. The diameter is 275 millimeters. The nominal pitch, which is used to set the initial pitch plane, is 300 millimeters. And what we have to do now is enter our R over R positions. I'm not going to enter in all the data, but I do want to manually show you entering one section here. What I also have to do is specify how many points per section. So since we had 13 points, I'm going to enter 13 for all 3 of these. And my data is in XYZ format, so that's important to select this here. When I go to the next page, I can now enter XYZ triplets of 3D data. And what I'll do is I'll start from the trailing edge and work my way to the leading edge. Now I'm going to take data from Excel, this data here, and I'm just going to paste it in. But you can manually enter this data. It's no different. And I accidentally put that in the face data, but it's okay. I'll take it and correct it. Here's the back. I paste this in. It's deriving an angle and a radius, and it's ensuring that everything is on the correct radius. We go here and we can see our foil shape. Now it's upside down because I probably had my orientation backwards. So I can go here, switch this, and we can go back, and now it's right side up. You can see that chord, thickness, pitch, skew position, and rake are all derived based on this orientation. The other thing that's interesting we're going to talk about in a second is the pitch plane. This is by default going through the nose and the tail, the mean position of each ordinate. But we can change this pitch plane to make it based on the face. We just have to select which points we want to use. So instead of using the mean, we would probably use the trailing edge point, and that pops this guy up to the baseline. And if we were using the leading edge, we wouldn't want to use the first point here, but maybe the second or third point in. So I select point 11, and now point 11 is on the surface here. We would proceed through and enter the data in for all of our R over R sections, everything that we specified in the table here. And just to show you what this looks like, I'm going to open up the file as prepared. Again, we can see all the different data. We go here and we get a preview of the section itself. All I'm doing now is I'm just flipping through, and we can see all the different data that's being derived. At this point, I would press build, and it would bring it right into PropCad, and we would have no issues here. Except that I forgot to enter the thickness value here, but it's okay. One moment, please. What happens is the data comes in and all the distributions are set to be entered and editable. There's no builder data that gets derived right away. Everything is set to be entered. But this gives us a chance to review our data and see how everything came in. If we click a column, we can get a nice graph of the pitch distribution in order to see that everything came in smoothly. This allows us to tweak and smooth data after we've brought it in from Scan Converter. So that's the basic process of pulling data into Scan Converter. Now quickly, I just want to discuss a few more things that can help aid you in bringing these geometries in from, say, a CAD file or an inspection device over through Scan Converter into PropCad. The first thing that we need, which I did incorrectly in this video, and we had to switch a setting in order to flip the section over, but it's very important to set up your coordinate system properly, particularly whether it's an inspection machine or a 3D CAD file. We want to make sure the X is the shaft axis, that it is coincident with the shaft axis, and we also want to make sure that the Y axis bisects the middle of our blade. Whatever orientation the blade is relative to the Y-axis, this will typically affect the drawing. So if you want a good drawing, be sure to set your blade up properly and align it with the Y-axis here. In polar coordinates, there's no real Y-axis, so you would use the 0 degree angle here, and you would line your blade up with that angle. And you only need to scan one blade. Typically, you could scan more to check variation between, but one blade is typically what's used in this process here. The other very important thing for Scan Converter is to choose an appropriate R over R distribution. Wherever there is curvature, whether it's the leading and trailing edges or maybe a fin at the tip of the propeller, or perhaps just a very bizarre rake distribution at the tip. You will need to increase the density of your radial positions as you have curvature in the surface, at least if you want to resolve that. Sometimes we'll do a very coarse R/R distribution just to get the basic features extracted out of the propeller. Sometimes we're not looking to fully recreate a propeller. We're looking to get the major parameters, the blade area, and the skew angle and things like that, so that we can build a smoother, improved variant. So depending on whether you're trying to do a full recreation or you're just trying to extract the parameters, you may or may not choose a more or less dense R/R distribution. This particular example, I used a Kaplan style propeller here to show that we really only need a 90% and a 100%. We don't need the intermediate 95%, 97.5%, etc. Because this has very little curvature at the tip, we can get away with a very coarse distribution. So thinking about the surface curvature and where you need sections, that's really important, and it can help dictate the success that you have with scan converter. The other thing that we touched on during the presentation was selecting the pitch plane. PropCad does its best to identify the pitch plane upon importing, but it mostly defaults to a nose-tail type pitch plane. That would be this bottom figure here, where the pitch plane is going through the nose of the propeller and the tail of the propeller. As we change which point is referenced, we can drop this pitch plane down. So we see while the lower one may have been how PropCad first interpreted the blade, it has a pitch of 332 millimeters. We can see that setting the pitch down to 300 is actually where how we want to represent this blade. And what this affects, besides just the calculation of rake and skew, this will affect the relative ordinates of the section. So you can see here, this point is at 4.8 millimeters positive above the baseline. If we shift that down here, this is now effectively at 0. Same thing here, the tail is effectively at 0 in this orientation. And as we drop it to a proper pitch plane, we see now the tail is at -5 millimeters. So this can be very important for getting not only a smooth pitch distribution, but properly laying out your section so that the cup is represented and different features like that. There's also an important issue of, again, it comes down to surface curvature. The face and the back do not have a lot of curvature in them, but right at the leading edge and the trailing edge, they do have a lot of curvature. And so if it's important for us to resolve this section shape, we want to make sure that we add additional points onto our scan right at the nose. I can show you quickly how this is done. We would just typically come in here. We have our points and our sections. I'm going to turn off these surfaces so we can see. And what we would do is we would just supplement adding a point in here by manually entering a few extra points. Let me see if I can just do this really quick. Turn on intersections. Boop, boop. So this is something that you may have to do in order to fully resolve the nose geometry here. In this particular case, this one is relatively sharp, but in most cases, it's a nice round nose, and therefore you'd really want to add points right on the edge here. And I think it's very apparent in the PowerPoint here. We can see that there's a lot more points added in here. Again, on this knuckle on the trailing edge, there's also a lot of additional points added in. So this can be really important. Again, if you're just trying to get some basic features out of the propeller, this isn't going to affect much. This doesn't affect the calculation of pitch. It doesn't affect the chord length. It just affects really the nose, hydrodynamics of this section. So depending on whether you're truly recreating this propeller or just using it to extract the parameters you need, that may dictate how much time you put into editing the points on the nose. And this is just highlighting those changes here. The other thing where we can kind of select this pitch plane here, we'll see that our choice of pitch plane affects the resultant data. So what I'm saying here is that pitch and cup are linked. If we look at this picture here, this shows a cup drop of -5 millimeters, where this doesn't show any cup drop. In fact, PropCad would interpret this as camber. So in this case, the camber is significantly less than this distance here. So this is important for selecting your pitch plane. Just remember, it's going to affect the cup drop and the camber calculations inside of PropCad. And what you'll want to do is you'll want to pull up graphs of pitch and graphs of cup, and you'll want to look for outliers. The pitch distribution is generally smooth, so we know that there shouldn't be a little bump in this. When we look at the cup, we see a bump in the cup also, and we know that typically cup is a constant drop for a large portion of the trailing edge. So we would expect that this would be a misidentified pitch plane. So if we change the orientation, kind of again like this here, we change the point that we select to get a better pitch plane. What happens is we'll see that this data goes away. It smooths out. The pitch or the cup is now smooth. The pitch is also now smooth. And you can use camber as another check as well. So this is a good way to ensure, do a sanity check that you've identified the pitch plane properly, and it'll allow you to smooth the data here. So that's kind of the end of what I have for recommendations for using Scan Converter. Let's review what we talked about today. We talked about PropCad Premium, the new edition of PropCad that is kind of focused on manufacturing and inspection, and part of that is Scan Converter for recreating patterns, existing designs, things like that. It really is an inspection utility. Scan Converter extracts features. We can fully recreate the propeller, or we can extract just the data that we're interested in, such as distributions of chord length or pitch. We can use data from a variety of sources, including inspection systems like the PropScan and the Hale MRI, published tables of offsets, 3D offsets that is, and we can also extract data directly out of CAD files. Scan Converter is really useful for recreating these designs, extracting parameters and data out of a design that you might want to reuse in a new model, and also reverse engineering legacy designs, patterns that have been covered in Bondo and hacked and sawed beyond recognition. It's a good way to kind of reverse engineer these old legacy designs that we have laying around that we'd like to use, but we really don't have a way of representing. There's no drawings or anything like that. So this allows us to take those designs, prepare drawings, tables of offsets, new patterns, and things like that. When using Scan Converter, you'll want to make sure that you properly orient the propeller in space, whether that's on your inspection device or within your CAD document. And you'll also want to choose an appropriate R/R distribution, typically with increasing density near the tip where curvature is very severe. You'll want to ensure that you add additional points on the leading and trailing edges if resolving the full section shape is critical to your process or your application in this case. We also discussed selecting pitch planes and how that affects the resulting data or the smoothness of the data that's resolved. And I discussed a few different ways that you can compare those distributions in order to make better selections of pitch plane or just smooth the data in general. Again, that's pretty much the end of the presentation here, but we are looking to support more manufacturers and more propeller builders as we progress forward with this PropCad Premium Edition. It is really geared towards manufacturing, whereas PropCad standard is going to be geared towards design. And coming up in March, we'll be having 2 days of PropCad training in Durham, New Hampshire, right next to the University of New Hampshire, at our office. The first day will be focused on PropCad standard and using the builder to create designs and design variants, preparing drawings, exporting to CAD CAM, while the second day will be focused exclusively on the premium features, the different inspection documents, the scan converter utility, and the pattern corrections utility. We'll spend a half day going through those on March 18th. So if you're interested, there's more information available on our website, hydrocompinc.com/PropCad best practices. You'll see a little bit of what you saw today, but it will be in much more depth, face-to-face, in an interactive, fun class. So if you're interested, visit our website. There's a registration form on there. We'd love to have you up here and spend some time going through PropCad together. Of course, we will be holding more webinars in the future. You can see our full webinar schedule and the rest of our training courses that we offer at hydrocompinc.com/online training. And you can see our upcoming trade show schedule. We'll be going to ITS for sure, and we'll have a stand there. So stay tuned as we get the details. We'll be publishing those on our website. Again, I want to thank everyone for their time today. And now we can move on to discussion and questions. I'm going to just pause stop the screen sharing for a minute, and we can begin questions.